Hey everyone, welcome back to another Latent Space Lightning Pod. This is Alessio, partner and CTO at Decibel, and I'm joined by Squix, founder of Smile AI.
Hey, today we are doing another lightning pod, but this time I think our first diffusion language model pod with Stefano Ermon from Inception. Welcome.
Thank you. Yeah, excited to be here.
So Inception, you've been making a little bit of noise with like diffusion models, over the last few months. But I think that the big one is now that you are actually competitive on coding tasks, and obviously the tokens per second is really impressive. So basically, like, could you tell us the overall story of Inception and maybe like why you're betting on diffusion language models?
Sure, yeah. So the story started back in 2019, actually. At that time, I've been doing research in generative models since basically 2014, 2015, when I started my faculty position at Stanford. I've been working on a variety of different kinds of generative models. But yeah, in 2019, I was working on image generation. And back then, the best generative models were GANs, generative adversarial networks. And we were pretty unhappy with GANs and how hard they were to train. And so we started pushing this idea of building a different kind of generative model with my student, Yang Song. And we kind of like showed that there was a better way of building image generative models and that you could train this diffusion kind of model that instead of generating images in one shot, it kind of like generates them through this iterative refinement procedure. And so we kind of like pushed out some of the first papers on diffusion models for image generation using deep neural networks. We used to call them score-based generative models. And that kind of like was picked up very quickly by industry, by folks at Stability, by Midjourney, and then kind of like became the state of the art for image generation, video generation, basically any kind of continuous modality. Diffusion models and variants of diffusion models are now the kind of like the best approach that exists. And since basically 2020, 2021, I've been trying to get diffusion models to work on discrete data, so text generation, code generation, DNA generation. And it's been really hard. After many years of trying, we were able to show that diffusion models, we figured out a way to train basically some kind of discrete diffusion model that was competitive with autoregressive models at small scales. And so we published a paper at ICML last year that won the Best Paper Award, showing that for the first time, basically discrete diffusion models were competitive on language generation with autoregressive models up to the GPT-2 kind of scale. And I got very excited about those results. And I really wanted to see what happens if you train bigger models on more data and you put all the kind of engineering efforts needed to really get to state-of-the-art results on tasks that matter. And so that's how Inception came along. And so I recruited some of my best former PhD students, a lot of Stanford folks. And then we started the company last summer. And yeah, we've been working on basically improving those research ideas that we had. And we've been successful in training the first commercial scale diffusion language models. We call this model Mercury. We released the first one, Mercury Coder, back in February. And we just announced a couple of weeks ago the first diffusion language model for more like chat, kind of like text use cases, so summarization, translation, reply prediction. And yeah, these models are really exciting. They are much faster than other aggressive models. They have some very interesting new capabilities. And we're excited about the future of this technology. I can see a world where in the future, all language models will be diffusion-based. I think it's a superior kind of like approach. And so I'm very excited to be at Inception working on this.
Can you maybe do a quick intro on diffusion models for discrete text? Because I think people have an understanding of image generation, which is you add the noise, you remove the noise, but it's kind of hard to grasp how you actually train a diffusion text model.
Yeah, it is actually a very similar kind of idea. Typical language models, LLMs, are autoregressive, meaning that they generate objects left to right, typically one token at a time, one word at a time. And you can do the same thing for image generation. Like you can generate images one pixel at a time. It's just not a very good idea to do that. Diffusion models, on the other hand, they work by generating objects kind of like in a coarse-to-fine way. You start with a rough guess what the answer should be, and then you refine it, again, using a neural network typically. And diffusion language models work the same way. You kind of like start with a guess of what the answer should be, and then you refine the answer using a neural network by modifying essentially multiple tokens effectively in parallel. That's kind of like the reason diffusion language models are much faster compared to autoregressive models, is that each neural network evaluation doesn't just give you one token, like in the typical autoregressive world, but it's able to output essentially or modify multiple tokens. And so that's where you get the speed ups, the fact that you're able to modify many things basically in parallel.
And so when you're creating a training data set for a diffusion model, what does it look like? Is it just a normal pre-training corpus, and then instead of masking a token, you're like, I don't know, what are you?
Yeah, so there is a lot of secret sauce involved, but roughly, the approach is similar. So you can start with the usual training data that you would use for training an autoregressive model. You have to specify a neural network, which could be the same kind of architecture that you would use for an autoregressive LLM. So it could be a transformer if you want. The difference is that instead of training it to predict the next token, you train it to denoise a piece of text or a piece of code. And there is different ways of adding noise or removing noise. In the case of images, you would typically add Gaussian noise and you would train the model to remove the noise, although other ways are possible. In the case of text, again, there is different mechanisms of adding noise. You could imagine masking out some parts of the sentence and then training the model to infill, to guess basically what the missing tokens were. Or you could imagine different kind of noise models where maybe you flip tokens, which is more similar to the Gaussian kind of case where you kind of like randomly flip some of the tokens, and then you train your neural network to basically fix these mistakes and correct this noisy data point and map it back to the clean data that you started from.
Yeah, I noticed that you you did publish a paper recently, I think yesterday, or something, where you confirmed that you're actually using transformers for at least the Mercury models, yeah? And basically, does it have to be trained end to end, or can you just take any existing open model backbone and do this process? Like, do you have to initialize from zero, basically, or can you sort of leverage off of existing other language models?
There have been attempts in the literature where people have tried basically using existing open source models and then kind of like fine tune them. The challenge is that, the training objective is quite different because you are training based on denoising as opposed to next token prediction. Diffusion models are not causal, and that is also kind of problematic. It's a big advantage of diffusion models that you don't have to be causal. You can actually look at the whole context to the left and to the right as you decide kind of like the edits that you want to do, which is giving, it's a very powerful thing if you think about how you generate objects, but that makes it quite difficult to adapt kind of like models that have been trained with causal masking to this new task. And so there have been attempts in the literature annealing the masks, the attention mask. Like there have been various tricks and attempts at doing that, but it's not straightforward.
Yeah. And then on the sort of the equivalent of contrastive loss or guidance or anything like that, does that require any innovations, or does it transfer over nicely from the image side?
Transfer over pretty nicely. You can do basically classifier guidance.
Basically, I'm just trying to see where you can shortcut, leverage off the existing open model ecosystem. But it sounds like you have to do everything from scratch. Like there's nothing to reuse.
Well, you can use architectures. I think that at least the shapes that can be leveraged. So you don't have to reinvent necessarily completely different neural network architectures. A lot of the data can be used. Like I think perhaps there are optimizations, and you can think about what kind of data sets work best for diffusion models. But it's pretty much compatible in terms of like the types of data that you would need to do pre-training, mid-training, post-training. It's all quite compatible, but you have to change. You have to innovate on the training losses, on the objectives, which is actually exciting because you can do things that are not possible without regressive models, and suddenly they become possible with diffusion models.
Yeah. Okay. So broadly stepping back a little bit, why do you think diffusion language models are working now? I think it's been talked about for a while, for the last maybe 3-4 years, but all the examples I've seen were always like very kind of, not like, is there a why now? Obviously you have some secret sauce, but like, I'm just trying to figure out, like, is there anything fundamental?
I mean, depends how you define fundamental. I think there was some math that has been developed in terms of like thinking about. I like to think of diffusion models in terms of like learning score functions and kind of like gradients, basically of probability density functions, which are not really well defined in the discrete world, but there are kind of like mathematical analogous objects that you can kind of train using denoising like objective, like score matching like objective. So there was some pretty fundamental math that had to be developed. Then there's also a lot of engineering and tricks that to build on top. And then I would also add the fact that, once somebody shows that it's possible, suddenly other people are much more incentivized to get their own thing to work. And I think everybody progresses more rapidly once there is kind of like a proof of concept that something is possible. And so, yeah, we've seen, the Google guys also have a model. So it's exciting to see that the field is really starting to pick up speed.
Yeah, amazing. Yeah, any thoughts on the Google side? Obviously you were working on this for a while. Was it a surprise?
I mean, I know they've been trying for a while too. It was great to see that. My understanding was that, I don't know exactly how they do it. I thought they were, I don't know exactly what's their recipe, what's their architecture, what's their model, but it seems to perform pretty well. It was exciting to see that at least some other player in the space was able to independently come up with a solution that actually works, because I'm pretty sure it's quite different from what we do at Inception. So yeah, it's exciting, I think.
Yeah, like to my knowledge, Gemini Diffusion hasn't been widely released yet, but like I'm curious how to test it. Like if you got Gemini Diffusion today, would you run anything? Is there any use case that you'd be very interested in? Any prompts, or I don't know how to evaluate a
So
diffusion
there is a
model?
playground. I think
For Gemini Diffusion? Oh, I didn't know that.
Yeah, there's a playground. Yeah. So you can play with it.
Okay.
It's
Okay.
pretty fun. It does a lot of infilling tasks pretty well, which is also kind of like what we are seeing. Diffusion models, not surprisingly, they work pretty well at infilling, where you really need to be able to use context to the left and to the right. Or autocomplete is one of the main use cases also for Mercury Coder. And it seems like their model is also doing pretty well at kind of editing, in painting kind of tasks. To me, they've released some benchmark numbers. They seem to be pretty close to the numbers that we were getting with the Mercury Coder back in back in early this year. So yeah, it's exciting to see that they've also been able to get this technology to work.
And to wrap on maybe the pre-training phase, is there also post-training in the same way that people do with normal LLMs? Well, not normal, but you know what I mean, with like instruction following and things like that. Does that work the same as those models, or is it different in diffusion?
So our pipelines, yeah, we have something similar in the sense that we also use, we can do basically SFT, and we can also do, we do reinforcement learning, RLHF, we do reinforcement learning from human feedback. Again, some of the algorithms have to change. For example, we have a DPO algorithm specialized for diffusion language models. I was one of the original authors of the DPO paper that was originally designed for LLMs, autoregressive LLMs. I worked on a paper extending DPO for diffusion models, more continuous diffusion models like image generation, video generation. And that's also been quite impactful. Like if you look at some of the papers that have been released on some of the leading open source image generative models based on diffusion, you can see that the DPO piece using human feedback to really align the models to human preferences is really important if you want to improve quality. And we've extended a variant of DPO to diffusion language models. And so we're actually also able to use preference data to fine tune the models. And, but yeah, basically we have pipelines that are compatible with the existing SFT and RLHF data sets. And we do that with customers. Like we often work with customers that have their own internal data sets. They want us to fine tune the models on their proprietary data, and we can easily do that. It's all pretty easy once they share the data with us. I think you're muted.
I think you're muted.
Maybe give people also an idea of, on the compute side, when it comes to pre-training, how different the scale is. And then as you move to inference, also what that looks like, both in terms of throughput, compute requirements, and also like context size. I don't know if there's much to say there, but if there's anything.
Yeah, so we're unfortunately, I'm not able to share much on the training side in terms of like the amount of compute or the number of tokens that we're using. On the inference side, what we're seeing is that diffusion models are much more efficient. we're actually able to Pareto dominate autoregressive models. If you think about the typical trade-off between throughput versus latency, which you kind of like can get by changing the inference parameters like the batch size and things like that. What we're seeing is that we're actually able to Pareto dominate autoregressive models. So for the same throughput, we can get better latency, or for the same latency, we can get better throughput. And so throughput basically means cost, effectively. So for the same cost, we can make the models go fast, or for the other way around.
Is that the killer use case of diffusion, or are the model also just better?
Right now, that's one of the real differentiating factors where we're seeing a lot of traction. Like a lot of our users care about latency. So we're seeing a lot of use cases that are latency sensitive. And so people really care about being able to give answers to their users quickly. Lots of applications where there is a real-time kind of like component, voice agents where you're interacting with a person in real time, or IDEs, or like vibe coding kind of things where you really want to be able to see results quickly, like maybe you're vibe coding a website or a UI. So lots of these use cases where speed matters. We're seeing a lot of traction. And it can mean two things. It can mean either just giving even faster results to the users to improve the experience, or sometimes the value proposition can be people are currently using small autoregressive models to meet the latency constraints. What you can do is you can put in a bigger diffusion language model that's going to be faster because it's a diffusion model, and it's going to be higher quality because it's a bigger model, it has just more parameters, been trained on more data. And so that's also been a very valuable kind of like use cases of diffusion language model.
How should people think about the Pareto frontier today as far as capability of model? I know you released some numbers on the Coder model, which is roughly the same as 4.0 Mini, Mistral Small 3. Anything else on non-coding, or maybe I missed it in all the announcements?
Yeah, it's been released recently. We had our generalist model evaluated by artificial analysis, and the intelligence score from AA artificial analysis is around 40. So it's comparable to GPT 4.1 Nano, Claude Haiku, kind of like closed source speed optimized models. It's roughly comparable in terms of intelligence, but significantly faster, 10x faster compared to this kind of speed optimized autoregressive models. We're working on next generation models that are going to be even more intelligent, but that's not currently publicly available.
Is there something, so if you think about use cases, is there something that people should not be using the fusion models for? Or this is just kind of, in your mind, it's like a superior, just swap everything over to these, and then as we scaled them, it's funny because you're seeing image generation go towards autoregressive models, and then you're seeing the text models go to the fusion. How do you kind of see the model use case match?
So the API is the same. It's like text in, text out. So in principle, any use cases that is supported by an autoregressive model is also supported by a diffusion language model. In terms of capabilities, yeah, as I mentioned, like we're not frontier level. And so there's certainly use cases where you probably wouldn't want to use a diffusion language model, or at least not the current existing diffusion language models. And so, yeah, I think at the moment it's more a function of kind of like what's the intelligence level, how much do you care about latency or cost. So there's definitely a bunch of use cases where diffusion language models are already competitive, they're already the best solution for those use cases. There are others that are still yet to come, and I think that will require scaling up and making further improvements to the training and the data and various kinds of things. I'm pretty optimistic about a future where diffusion models can become the dominant solution. I've seen it happen before with GANs a few years ago, so I wouldn't be surprised if that's the case also here. I really like this idea of using context to the left and to the right, the fact that you have error correction that is built in. So you think about an autoregressive model, once you output something, you can never take it back. And so if you want to if you want to fix mistakes, maybe you can do a reasoning chain, maybe you can do it that way, but it's kind of unnatural, it's kind of clunky. The fusion model has this nice thing of kind of like fixing mistakes as you go. So I think it's going to be pretty exciting once we have next generation models, maybe with reasoning built in. I think we're going to see some very interesting capabilities emerge there.
Yeah. So in your mind, it's just a scaling question left, not a, missing capabilities from the architecture or like limitations of it.
Right. Yeah. No, and I think there is going to be potentially new improvements that can be. I mean, I'm sure that we're still pretty far from a local optimum. Like if you think about autoregressive LLMs, people have been trying all kinds of things, and so maybe there's not that many low-hanging fruits. What is exciting to me as a researcher and as an engineer, if I think about diffusion language models, it's all very new. We have something that already works pretty well, but I'm sure that there is a lot of design choices that were suboptimal. There is still a lot of ideas to be discovered, and so there could be big leaps, big improvements possible just by doing R&D on the way we train the models, the way we do inference. You have a lot more knobs. It's a different design space, so there is a lot of exciting R&D to be done, and we're seeing it even at the company. Like the improvements that we're seeing week over week are pretty substantial, and so it's I'm personally very excited about this.
Yeah, awesome. One more thing about on the inference side, I think a lot of people are very cognizant of the serving requirements between autoregressive and diffusion. A lot of people rely on the batching characteristics in production. You would not have that, right? Are you aiming to are you aiming to abstract that problem away for people, or are you just going to release the models in open weights and then people will deal with it however they want?
So we don't have a plan at the moment to release models to open source any model. And in fact, it's a little bit tricky even if we wanted to release, let's say, a small, maybe less capable version of the models, we'd have to release the inference code, which is also proprietary. Unlike an autoregressive model where the inference code is kind of like straightforward, there's not that many ways you can do inference. In an autoregressive model, you can tweak a little bit the sampling, but it's pretty straightforward. In a diffusion language model, there is a lot more knobs and a lot more innovation that can happen on the inference side. And so it's very hard for us to open source a model because we'd have to release the inference code. And by the way, we have our own inference engine. So just like you would normally serve an LLM using a VLLM or SGLang or TensorRT LLM, we have built our own inference engine. And so we are supporting production traffic already with our own inference engine. We support continuous batching, quantization. Like we support a lot of the features that are supported in these serving engines, caching, like prefix caching, like a lot of that stuff is already handled by our own serving engine. But yeah, it gets a little bit tricky if we wanted to open source because a lot of the IP is around on the inference side as well.
We have a bunch of inference nerds listening to us and who might be interested in joining you. Like what's one underappreciated problem or something interesting that has come out of this production work?
There is a lot of, just like the workloads look different, and there is different opportunities for optimizing aspects of the serving, the way we serve models. So yeah, we have a bunch of smart people that are kind of like working like MLCs, I would call them. I think, I've been working in this space for a while with students at Stanford. I was on the flash attention paper. So I've been focusing on these kind of issues for a long time. And the things you see once you start using additional language models are quite different. So there is new opportunities for optimizing the models, the inference algorithms, the way we implement them, and we write kernels to really make them go fast. So there is a lot of exciting opportunities for doing work. And yeah, if you're interested, reach out to us. We're hiring at all levels. So I'll use this opportunity to do this plug for applying to our jobs.
Yeah, absolutely. I mean, this is, if we can get people a job, if we can get you an engineer, I think that's a win for us doing this, right? Okay, so I want to move on a little bit in terms of like we let's say we have production and high quality LLMs. You made an interesting controversial statement earlier that you said most frontier models or most language models will use diffusion in the future. I don't think that's consensus. Could you just elaborate why?
I think that there is a chance. I mean, I don't know if that's going to happen, but I feel that there is a world where that could happen. And I think it could be driven. If it happens, it's going to be driven by efficiency. Like we're all constrained by essentially power. And if you have, I mean, at the end of the day, it's all an inference game, right? Okay, training is expensive, but then the thing that matters is being able to serve these models cheaply and without consuming more energy that we have access to. And you only have so many gigawatts of power and so many data centers. And there is a growing demand for tokens that you need to be able to serve to users and all kinds of apps that are being built. And so there is a real need to find a solution that can give us maybe a 10x improvement on the efficiency side, and there's a really good chance that diffusion models are the thing. So if indeed it's possible to match the quality of frontier models in terms of quality, if you have a win on the inference side, that is going to be the solution that will be deployed, right? Because it's at the end of the day, it matters. There is a real resource constraint, and so the better solution will be deployed and will win and will be scaled up.
Yeah. I would just note that it's interesting that you guys on your paper, you noted that your context length goes up to 128K tokens and you use normal training recipes. That is the one thing, if I think about autoregressive versus diffusion, that you don't have a cache that you can pre-fill, but I'm sure you figured it out somehow, right? Like that, but I think that's kind of cool that just translates over.
Yeah, there are interesting caching strategies that can be implemented, including some that have been in papers. There is some growing literature on KV cache-like mechanisms for diffusion language models. And so you can find something in the literature as well from NVIDIA, from academic groups. So there's definitely a lot of optimizations that can be done.
Yeah. So I would say like quality, it's anyone's game. It's really going to be amount of compute, data, all that, not necessarily driven by just the algorithm itself. But like I think you unlock a lot of different use cases, which is very cool. And it's interesting that you released the chat tune model because actually maybe the focus should be everything but chat. Like chat, fine, autoregressive, right? Back and forth, like sequential, okay. But like everything else, like nobody's releasing any base models. And actually you can offer something very different there. That would be my pitch to you in terms of like, you don't have to fight with autoregressive language models head to head on quality. Actually, you can just do everything else because they cannot do it.
Yeah, for sure. Yeah, I think we're definitely, exploring in the market, working with customers, figuring out where we have an edge, with other use cases where we're particularly good compared to autoregressive models, capabilities that are just not, like, for example, around controllability, like, or thinking about hallucinations, error control. Like, there's all kinds of interesting things that are in theory possible with diffusion language models. And so we're also excited to explore that. It's a lot easier to provide an OpenAI compatible endpoint that anybody can build on top of.
Yeah. That's the industry standard. I mean, I think there's a demand for new form factors and new capabilities, and that would be your relative strength,
Sure.
So I think you mentioned customers. Yeah, I think that the last thing I wanted to touch on was just what kind of customers are you looking for and that you're ideal for? Like if someone says, I have this problem, they should come to you. What is that problem?
Yeah, whenever they have applications where they are not able to get the level of quality they need from existing models, typically because they need to use one of these closed source speed optimized models, or they're fine-tuning a small autoregressive model. So any kind of applications that is latency constrained where customers are not able to get the quality that they need, diffusion language models can be a great alternative. We can increase the quality of the answers by plugging in a bigger model, or we can make the existing kind of form factors go much faster and increase the user experience and improve the user experience. So any kind of like latency sensitive applications of LLMs, diffusion models right now have a real edge.
Yeah, amazing.
Stefano, thanks for coming on.
Yeah, thanks for having me. Yeah, it was really good to meet you.